Hey everyone, so we're going to go back to limits because there is a theorem that we're going to be using to find the limit of something that's in an indeterminate form. So pause the video and do the do now. All right, so which of the following statements is true? So they're asking f of 2 exists. The limit exists. Well, I would say that's true. The graph of f is shown. Which of the following... Oh, is false. Well, f of 2 exists. The limit exists. That's true. 3, the limit exists. 4, the limit does not exist. 5, the limit exists. The function f is continuous at 3. Yep, so it's C. The limit exists at 2, but it's not continuous. At 3, it's continuous, not differentiable. 4, the limit does not exist. 5, everything's true. Okay, so a little history lesson. So the rule we're learning about today is called Lhopitals rule. So that's this guy. So this guy was a rich guy, right? And he wasn't very good at math. And there were the Bernoulli brothers. So these are the Bernoulli brothers on the right. Now, Jacob Bernoulli was super famous. He was really well known as being really good at math, famous mathematician. And Johann was also very good at math, but he was kind of like the lesser of the two brothers. I think there were more siblings also who were really good at math. So what happened was L'Hopital was this rich guy, and he hired Johann to help him do some mathematics. And Johann proved this theorem that we're going to learn about today. But he sold it to L'Hopital. He's like, I'm going to get my money on. So he sold it to L'Hopital. So it's called L'Hopital's rule, but L'Hopital didn't actually create it. Johann did. Now, the funny thing is, when L'Hopital died, Johann was like, oh, hey guys, I actually made this. And everyone was like, no, you're the dumb Bernoulli. That's not real. And I think it wasn't until after Johann died that they actually found out that Johann Bernoulli really was smart and just as good as Jacob, even though Jacob was known as the number one Bernoulli brother. Okay, so just a quick reminder of an indeterminate form. Indeterminate form is something that's a 0 over 0 or infinity over infinity. So we've talked about that before. Okay, so who remembers the answer to this? So this, we just looked at the picture. We didn't have a way to do it before. When we just memorized that it's 1, right, by looking at the graph. All right, so here's L'Hopital's rule. That was not made by L'Hopital, but Johann Bernoulli. If two functions are differentiable and except at possibly C, and the derivatives are not equal to 0, then if you get an indeterminate form, 0 over 0 or infinity over infinity, what you can do is just take the derivative of the numerator, the derivative of the denominator, and then take the limit. And it'll be the same limit, right? The limit is the same. Now notice here, it's the derivative is on the top, the derivative on the bottom. It's not a quotient rule. All right, so I'm going to prove this to you. All right, so the limit of f of x is 0 as x approaches c. I guess that part disappeared. X approaches c. And, then f of x equals 0 and g of c equals 0 since f and g are continuous. So I have this limit, so now I'm going to rewrite it. Now, if this is a derivative, how do you write the derivative of f of x? So that is the limit of f of x minus f of c over x minus c all over the limit as x approaches c of g of x minus g of c all over x minus c. So I just rewrote it using the definition because this is f prime, right? So then notice what happens. These denominators cancel. So I have the limit as x approaches c of f of x minus f of c all over the limit as x approaches c of g of x minus g of c. But look back at the problem. What does f of c equal? F of c equals 0. So this is 0, and this is 0. So we get the limit as x approaches c of f of x over g of x. So it's kind of backwards, right? So the derivative of the original function equals the derivative. The limit of the original function equals the limit of the derivative of the top divided by the derivative of the bottom. All right. So here's another problem that we looked at, and we when we first started limits, but we had no way to do it. We just looked at the calculator and we're like, okay, what are these numbers? This is backwards. 0.001 is 0.995. These are not going closer to 0. These should be reversed. Oh well. I'm just going to write them in like where they are supposed to be. 0.995 and negative 0.1 is 0.956. And then this one, 1.05, 1.005, and 1.0005. Sorry, these are in the, I don't know what I was thinking when I typed this. The whole idea, though, is we get closer to 0, we equal 1, right? Now, if we use Lhopitals' rule, though, what's the derivative of the numerator? That's just e to the x over, what's the derivative of the denominator? 1. Now we can plug in e to the 0 equals 1. So by using Lhopitals' rule, we can figure out that the answer is 1. All right. So now before we had these terrible things we had to do, right? If we try to plug in, we get 0 over 0, and you should always check that. Right? So we're going to write the limit as x approaches 0. What's the derivative of tan x? Secant squared all over 6. What is secant of 0? Well, what's cosine of 0 is 1, so it's 1 over 1 over 6, so 1/6. Again, plug in. What do we get? We get 0 minus 0 over 0. So it's in an indeterminate form. So we're going to do the limit as x approaches 0. Derivative of the top is cosine x minus 1 all over 2x. Plug in. What do we get? 1 minus 1 over... we get 0 over 0 again. So what do you think we should do? We're going to take the derivative again. So the limit as x approaches 0, derivative of the top is negative sign over 2. That gives us negative 0 over 2, so our answer is 0. Right. Way easier than what we were doing before. All right, try these on your own. So, same thing as the 0, but it's with infinity. We get infinity over infinity. So we're going to rewrite it as the limit as x approaches infinity. Derivative ln of x is 1 over x all over 1. That's 1 over infinity, so that's 0. Again, we get infinity over infinity. So we're going to take the derivative of the top, derivative of the bottom. Derivative of e to the x is just e to the x over 1. So we get e to the infinity, which is infinity in this case. Infinity over infinity again, so we're going to take the derivative. 1 over e to the x. That's 1 over infinity, which is 0. All right, now here's a hard one. Now, if you notice, if you plug in 0, you get 0 over 0. Now, if you notice the denominator, what will we have there? We have a product rule. You really want to avoid a product rule. This one's a little gross, so before we try to take the derivative, honestly, it's not going to help. I don't think it's going to help to take the derivative. So we're going to go through and we are going to simplify this thing. So tan is sine over cosine minus, and then common denominator, right? Cosine, sine, cosine. So then I can factor out sine x, 1 minus cosine x, all over cosine x. Sorry, that's super messy. So I made a common denominator, and I factored out the sines, right? Now the denominator, this is x squared times sine x over cosine x. So this whole thing is x squared sine x over cosine x. Now, notice we can cancel now. So those cosines cancel and the sine cancels. So we end up with the limit as x approaches 0, 1 minus cosine x over x squared. Now, if we plug in here, we still get our 0 over 0. But this is an easier Lhopitals rule. So I'm going to take the derivative. Let's see, we get sine x over 2x. Plug in 0 over 0. One more time. Cosine x over 2. So that's 1/2, right? That's hard, right? That's a tough one. So I rewrote it as best I could, basically just hoping for the best, and then I put it together. And then I took the derivative used Lhopitals rule. All right, so now this one is a little different. Now, do we get an indeterminate form if we plug in? We don't. 1 over 0 is not an indeterminate form. So we need to create a common denominator and put this thing together. So it's going to be the limit as x approaches 0 from the right. Okay, so common denominator is x sine x. And then the top becomes sine x minus x, right? Times x, sine. Okay. So now if I plug in, I get 0 over 0. Now I know I'm basically breaking the rule I just told you, which is not to do a product rule, but I think we're stuck and we have to do a product rule here. So let's go through and do that. So it's the limit x approaches 0 from the right. Let's see, the top is cosine of x minus 1 over derivative of the first times the second plus the first derivative of the second. We get 0 over 0 again, right? 1 minus 1 on top over 0 plus 0. So let's do this one more time. Hopefully, I think we're done after this. Derivative of the top. Derivative of the bottom. So cosine x and then a product rule. Cosine x, x negative sine x. Yeah, so here we get 0 on top, but we get 1 plus 1 plus 0 on the bottom. So 0 over 2 is 0. And now we're done. All right, that's it. Do your homework. Do your homework before going on to the next video, please.